Good day to you. This is Admiral of a landlocked nation of Bhutan. I am the Admiral of Bhutan today, I've decided. Yes, the last video was a prescribed rant. I've allotted about 1 out of 3 videos to a pure rant in order to toot my own horn because I live alone. Been living alone for 16 years. So I do some pretty crazy stunts, man, but it's all for a good cause. All right. Over here, you'll see our current object of study. And this is important, although I don't want to be tedious and just like, oh my God, click and on to the next video opportunity. This is not working out at all. Let's just take a good look at this. Maybe center it a little. So you can see that that is 3 curves. Now I promised to give this video, and the rant was simply to let you know that this is going to be profound, but it is also going to be simple. And that's the beauty of geometry. You are looking at pure mathematics here. Every single one of those curves has an exact equation. Now it is in linear algebra, so you have to understand you're using straight lines to measure curves. And that does bring up an interesting topic. How in the world do you do that? Well, that's not what we're going to talk about, because I would have to admit that does sound tedious. And there's the full image where you can see these 2 lines here, and I'm getting my pointer. There's my pointer. This is a typical hyperbola, which you can probably guess is just one of a family of hyperbole, because it could be the official word for what I'm trying to describe is its eccentricity. It could be more flattened so that the blue line, instead of going off like this, would go off more horizontally down. And so the hyperbola would essentially collapse in the horizontal direction until it's more thin going up, but you can also contract it so that it gets more eccentricity. It depends on how you assign valence to the eccentricity, either more or less eccentricity, as it opens either out or in. With the two end lines, you see this is a symmetry. It goes up and down. The ellipse does also, but both of these, all 3 of these objects have a characteristic in common. They're all curved. There is a special case of the family of curves, which is what you're looking at. The entire family of curves is here on a plane. But a straight line is when the hyperbola opens out so far that it snaps to a straight line. And it would have to snap because at infinity on the asymptotic relationship, to broaden that term just a little bit, the hyperbola will never go vertical. It always goes off to infinity, in this case to the left. And if it goes up, it goes off to the northwest. And if it goes off down south, it goes to the southwest. But you could see that all of this could be flipped. So it does have a mirror symmetry on the plane. All of these objects do. You can see that they're symmetrical. How so? They're symmetrical around the horizontal axis, which means that they open up and down. Now, all of this is grade school stuff, and I will undon this rather uncharacteristic of Bhutan hat. This is a Bhutan robe, and it is a little chilly here at dawn here on the last day of May in Chico, California. The family of ellipses is shown by the red, and you can see that also could be stretched horizontally. And if you kept going stretching the ellipse horizontally until it was thinner and thinner, it would snap to a straight line. That snap that I'm talking about is called a quantum jump. That's a quantum jump. It's a discontinuity in a continuity. That is called a quantum jump. It's the basis of the metricization of the line for distance, is the quantum jump from 0 to 1 on the unit. That is at the smallest scale, given a specific name. In physical space, it is assigned the name Planck unit, which is the smallest measurable unit. But in order to have a smallest measurable unit, there has to be a jump from the origin of the unit to the unit. And that's called the quantum jump of that geometric space. On the line, it's from 0 to 1 to get the counter for the index, which is the smallest division that you make on the line to quantize the line to have a distance metric, which is positive. So distance is a positively oriented linear metric. This is curvature, not linearity. And what's the difference? You can see the difference, and if I were to switch screens here so that you can see this in a slightly different fashion, it's now oriented so that it's symmetrical around the vertical axis. Let's just look at that quickly. Flash, that is oriented around the horizontal axis because it opens up and down. This family of curves is oriented so that you see it rotated 90 degrees in the counterclockwise direction. So now we're introducing angle, and this introduces momentum, because whenever you say angle, you are implying, perhaps, depending on the context, angular momentum. Momentum is introduced to introduce dynamics. You could say dynamics and mechanics are dualistic terms because you can't really have one without the other, because you're seeing the same thing from two slightly different points of view. And that is the difference between dynamics, which is what we want, and mechanics, which is the numeric aspect of dynamics when you're measuring change. Now, mechanics perforce measures change, but you're either trying to get the end of the change, which is usually a position, but you may be studying the process, which may be continuous. And that leads us to the quantum paradox. The quantum jump in physical space occurs either in an electron or a photon. That could be extended. There is a broad footnote because this is an exploratory field. It's currently being explored. Why? Because we don't have the solution that we demand. Which is what? We're looking for the structure of the universe at the smallest scale. I have determined, and this is rather well known, so I won't say that I discovered this certainly, but you can't actually probe that is curvature, to the limit that you want if you're using an extrinsic geometry, which is what linear geometry is. It's Euclidean, based on the axiomatic point, which gives the quantization unit for the line. And that's how Euclid began his very famous book, actually the most famous book of all time, Elements. The first two sentences of Elements should be memorized by anybody who wants to know what geometry is, because Euclid essentially invented it. And more than that, by the way, that is an overstatement. He didn't actually invent geometry, but it does depend on your point of view. I say he did, but I reinvented it because he made a mistake in his axiomatic step. He made a tremendous breakthrough in human logic by realizing that in order to define the line, which is what he wanted to define and succeeded in doing, but in order to define the line, he had to take a step backwards and define a point. And that's the first sentence in the most famous book in all of science, is the definition of a linear point. And it is linear. And you have to say that. I discovered really what's obvious. You could say I discovered the obvious. You are preferring a very specific reference frame when you choose to begin with a line on the plane. You could begin with this, which is the family of curves. You may be able to spot the circle in this, but if you look hard, you'll see there actually is no explicit circle. There is an explicit straight line, which is called the directrix. It's a Latin word which ends in ix. But that black line at the bottom, where it says E equals infinity, that's the eccentricity is now infinite because it's opened up fully downward. If you picture that from the blue line with its two fanning arms, curved arms going to two infinities. If you lower the two infinities so that you increase the eccentricity, which currently is at 2, the green line is the parabola, and that's E equals 1. That's a balance point in planar curve space. After that, the parabola snaps to an ellipse. But actually, it has to pass through a phase in order to do that. This is called an evolute, and this is the proper mathematical geometric use of the word evolution. You're seeing the evolution of a straight line to a circle. So the straight line is essentially two infinities in polar directions, and then you lift it. In order to make the first lift, there does have to be a quantum of lift. It will be an infinite lift, and so this is purely imaginary, but that's exactly what Kepler did. This is from Kepler. This is also from Newton. And we're going to look at that. It's also from Boschkovich. All three of these men did exactly the same thing in three slightly different ways. The evolute of a straight line to a circle. The evolute of an open line on the plane, which is Euclidean geometry, is based on that line, which is based on the definition of a point. You can lift the two edges, and that instantly, on the quantum jump, off the two infinities going up, you use an infinite amount of force to make the smallest first continuous move. There is continuity, but in order to have a metric, you have to assign a number, otherwise you can't measure the distance. So you have to have a 0. And that's the Cartesian grid overlaid onto the plane. A vertical line for the vertical aspect, and a horizontal line for the horizontal aspect. That's forced out of Euclidean systematic linear space. When you begin with a point which defines the quantum of the line, that's the quantum of the line, is the Euclidean point, because it's the smallest part. And the parts are separated. What are they separated by? It's undefined, but it ends up being distance. So the separation between 0, the origin, where you begin your measurement to get the index of the metric so that you can measure light years to a star, you have to have some kind of smallest unit. If you're using light years, that's quite a long ways, but it is also a measure of time, 1 year. Can you reduce it to a second? Yes, and that is to normalize the units. The second is an international unit, which is an arbitrary unit of both time and space, have an arbitrary unit, but it's based on the unity of time on the second. So if there's motion, which there is when there's curvature, that's what curvature is. It's the implication of motion in the system, which does not occur on the line. The line has no concept of motion, although you can manipulate the linear sequence, which is evenly spaced units all the way to infinity of some metric unit, which would be 1 of something. And if you have 1 light second, that is a unit of distance that incorporates the notion of time. And that's, of course, space-time. It's everywhere. We've always used space-time. It takes a certain amount of time to go a distance. Well, then you have space-time, because it took time to go that distance. So when you go that distance, for instance, the distance light travels in a year, then you've gone that distance, but it took a year to do it. That's called relativity. The curvature is the extension of the concept of linearity into general planar space, which collapses to a circle, because that's the smallest, well, it's actually the most compact closed line. You can see that the closed lines begin on the ellipse, which is a family. And if you open the ellipse, it snaps to a parabola. And that's constant. There's only one parabola. There's a family of ellipses. They can be stretched this way. They can be stretched this way. There's a family of hyperbole. The way it stretches is only in one direction, but there's a reflection. And down below you see its reflection. The hyperbola is a split object, and it's reflected around basically a parallel of the horizontal axis in this orientation. So the straight line is oriented horizontally. That's the basis of science. That's the basis of mathematical science, is that straight line. And the reason is that the linear number system is embedded in that line. That was proved by John Horton Conway in the late 20th century. So I, having found out all of these facts about this curvature, was able to make some deductions about the circle, which is the basic unit of the plane that is in a certain way opposite of the straight line. If you use the straight line to metricize the plane, you need two of them at an orthogonal angle. It turns out that's magic. That's called Euclidean geometry. But if you refuse to do that because you suspect that Euclid didn't go far enough in his axiomatic regression, where he wanted to define the line, but he ended up defining the point first, and that's the first sentence. The second sentence, in elements, is the definition of a line, which is a jump from 0D to 1D. Did he use that language? In ancient Greek he did, yeah. So he knew that the point is not really there, because it has no actual existence in space. The line does. And so the line has to be made of points. And it is. And that's where we get our linear number system. It's identical with the straight line. In order to parameterize the plane, what is meant by parameterization would need to be more carefully defined, but in general, the definition of the parameterization of the plane is the extension of the concept of distance so you can get a straight line distance, but at an angle. Because now it's on a plane, it's not 1D. You can get distance on a line, that's what the line is for, that's the metric of the line. The metric is what it does. The unit of the metric is the smallest division, in this case on the line, whereby you now can measure distance. That's what a metric does, it measures distance. Can you measure distance on a curve? Technically speaking, no, because there's no straight line anywhere. And so you have to use calculus to get a rate. And that's what Newton and Leibniz discovered, but Archimedes had already figured out the method of exhaustion back in Greek times. So we are talking about a transformation that needs to be made in order to extend the concept of distance to the plane. What we actually want, certainly for space travel, is extension of the concept of distance to what we call 3D, which is the addition of depth to the plane. And that also defines the two modes in which a human sees, one of which has no depth perception, which is what you're looking at on a computer screen called a flat screen image. That is a plane. So that is what we see. But we also perceive depth. We perceive depth in a different way than we perceive what our mind directly registers on a surface. You don't see the depth, otherwise a movie would confuse you, because it doesn't have any depth. My image here on the screen, this entire screen you're looking at, of course, is on a planar surface. That is what you see. That's why it looks real. But your mind will add the concept of depth based on clues. And this is discovered in physiology in the 20th century. It's a major breakthrough in our understanding of vision. So we do see in 3D, which is an amazing statement justifying all the work of Euclid at the physiological level. It's an exact match on vision. However, it does leave out the other aspect of vision on which there is no direct match because it's dynamic. It moves. There's motion. And the way we interpret motion in order to get a metric of motion is time. You have to have time to measure motion. And that's why Einstein's formulation of space-time is so critically important to advanced understanding, which is, of course, what you seek. I will attempt to provide a window into that advanced understanding of what is the tremendous breakthrough that Einstein made with space-time. It can be expressed geometrically, and it can be expressed mathematically, and it can also be expressed physically. It's a definition of gravity, and it's a definition of gravity on a proportion. And this is a very interesting formulation of space-time to interpret it as a visualization of gravity, because in order to do so, something has to bend. And it's space that is considered to be bending. In the hyperbolic diagram, which is projected down from 4D down to 2D so we can see it, I won't show it right now, but you can visualize it. It's called the light cone. Well, that is the basis of all the conics. What is extracted from the light cone, which is a 45-degree cone going up and down. When it opens down, that's the past. As it opens up, that's the future. Why a 45-degree angle? That's the exact ratio of time to space. In hyperbolic space, as a 45-degree angle is the relationship of time to space. It takes quite a bit of effort to get used to reading a space-time diagram. And it leads to all kinds of paradoxes because, of course, you're also seeing into an invisible realm. We are now dealing with imaginarity, but in order to understand what this imaginary realm is, which is the basis of this video, it is a geometric space. It does actually exist in a conception. So there is such a thing as imaginary space. There would have to be, or there would be nowhere to put infinity, because infinity, no matter how it's defined, and there are three major ways of defining the classes of infinity. One is spatial, one is temporal, but there's a third one as well. But all of this is captured in what is called pseudo-hyperboloid 4D geometry, which incorporates an imaginary vector, and it actually is imaginary because time is imaginary. With respect to space it is, but they have a direct relation. That's what Einstein discovered, is the direct relationship between time and space, which is what? Time lag. It's time lag. When you measure the distance to a star in light years, you're measuring time lag. That's why the year is in there, because that's how long it takes. That's the metric of time. Built into distance, there's a direct relationship. A direct relationship between the distance covered and the time lag. Time lag is very interesting because it leads you into the concept of relativity, because now you have two locations of time. And that means that the position of what you're getting a fix on has changed. By the time you see something, it's not there. It's gone in, you're seeing it in an imaginary space. It's not actually there. Physically, it can be proved that it's not where you see it. If it's 4 light years away to the nearest star, it took 4 years for that light to reach the Earth. Well, when it reaches the Earth after 4 years, in that 4-year time lag, the star has moved. You've moved and the star moved, so it's a co-moving reference frame. Well, that means that it's dynamic. That's relativity. It's dynamic space. That space, you can say that space has a time component. That's what he did. They're orthogonal. They're orthogonal. That's why it's the fourth vector, because it's orthogonal with the other three. But the other three fill space. Well, so it's imaginary. Well, he said that imaginary space is time. That's actually incorrect, but it's correct on a superposition, because he got the linear solution. If you linearize time, which is exactly what he did, can time be linearized? It depends on your reference frame whether you can linearize time or not. He said you can, and he proved it, so it can be. You can linearize time. With reference to space, time is linear, because space is linear. You're measuring a linear distance. Well, that's a one-component number. A distance is a positive, you could say real number is what, but that's just it's a linear number. It's a one-component number, a distance on a line to a star. But that line is essentially traveling partly through imaginary space, because in the time it took, see that photon, you can think of it as a photon traveling for 4 years. Well, while it's traveling, if you check the relative positions of first Earth, it is already definitely moved since the photon left. But so when the photon arrives, it reports where it came from on that line. which means that it expanded as a sphere. A moment's thought will convince you of that. That was actually proved by Christian Huygens back in the time of Newton. They were contemporaries, but Huygens was in optics mostly, whereas Newton was really more of a general scientist who was working on really the mechanics and dynamics of the universe. Sure, he was. At all scales, he tried and was rather successful with gravity, we all agree. Well, Einstein said gravity is all well and good. He uses Newtonian gravity in order to equate Newtonian gravity with the curvature of space-time. And here's not the curvature of just space. It's the curvature of space-time as a fabric, which means that time is bent in this reference frame. It's bent hyperbolically. So that leads us into the family of curves, because Einstein found out that he could use this family of curves in order to compose space-time. It uses this blue line system called hyperbolic geometry. The red line is called elliptical geometry, and this commonly conceded. You can look this up using a chatbot or just the normal mode of looking things up, and you'll find out that geometry is neatly divided into Euclidean, and Euclidean is what's used by science for computation, well, until about the 19th century, in which case we started using what's called transcendental geometry, which is essentially just 4D. Well, Einstein used 4D. Well, it's still orthogonality. You still have to use the Pythagorean theorem to get a distance in hyperspace. And that's what he discovered, is hyperspace. But it's the linear solution. What I discovered is the spherical solution. And that's in volume space. It's actually the hyperspheric solution because it is a hypersphere. The universe is not made of cubes, it's not made of hypercubes, and it's not pseudo-hyperboloid. Although you can prove that it is if you use Einstein's approach, because it turns out that the derivative of energy, which is the time derivative of energy or the space derivative of energy, is either position or momentum for energy. What you want is the momentum of energy, because that's what energy is. It's angular momentum, and that's a circle. So the angular momentum of an electron cannot be computed with linear geometry because it uses straight lines which don't match the curvature of the space. It's really that simple, and you would expect that Einstein knew that, but he didn't know geometry. He didn't know any other way to solve the linear equation to do what he did in inventing space-time and really introducing us to relativity, which is time lag. And now, since space-time is curved, and that's the fabric of the universe, it's inside-out hyperboloid, really nonsense, but it's not nonsense if you're trying to navigate in space. If you're trying to astrogate, which is to navigate the solar system, that's an old word, I just revived it. If you're trying to get to a planet with a probe, like for instance land men on the moon, or really, in a more realistic case, to go to Mars, you're going to have to deal with that distance relativistically for your signal communications, which is redundant. A signal takes time to reach Mars. You know how long? It's a long time. It takes seconds to reach the moon, to bounce a message back, and that's why when men landed on the moon, there was a time lag. As they spoke, you could not hear them. Well, you actually, when Houston would speak to the lunar commanders, there was a time lag before they heard it and a time lag before their response came back, amounting to about 5 seconds, which is quite a lag if you're used to TV, blip, 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 just going right by. No, not in outer space. There's a time lag for everything, for light. So all of that is curvature. How did he get curvature into his hypercubic system? He used hypercalculus, which he invented. It took him 10 years to invent hypercalculus, which only a supercomputer can do efficiently. It's not a human task. God knows how Einstein figured this out. But it is the world's most difficult equation to unravel. If you wish to do so, you can. There's an excellent teacher. He has a 3-hour presentation. I watched it twice, and I'm glad I watched it the second time. He'll tell you how to figure out the Einstein field equation mathematically so you finally understand it. But you'll wish you hadn't. Because it comes to a point where it's like, No, not the gamma term. Oh yeah, partial derivative just spreads out. You can't do it. But you can see that logically it could be computed. If you figure out all of these really long equations, which actually is very, very difficult to even conceptualize. Do it on pad and paper or on the blackboard? Nope. That cannot be done. Only a supercomputer can do that. That's why supercomputers just coincidentally, synchronistically came into existence about the time that men were landing on the moon. And without computers, they could not have done so. There was an onboard computer, too, for navigation, which got gimbal lock because the Houston engineers, if you want to put it that way, did not understand curvature geometry. They just didn't know what the hell they were doing. It had almost killed 2 of our cosmonauts. They're cosmonauts because Yuri Gagarin was first man in outer space. So they have dibs on the choice between astronaut. No, a white supremacist nation will choose whatever the fuck they want, and fuck Yuri Gagarin. So, I'm sorry, a little emotion there, but I am wearing the robe. I'm allowed to pontificate from time to time. This is a Bhutan robe. So, it's starting to warm up. The sun is coming up here. So, we're talking about the family of curves for which I've discovered the correct axiomatic basis, basically becoming really the successor of Euclid. So, I hope you're prepared for that. I'm going to make it simple, because true science is always simple. That's what makes it profound and worth knowing. It's for humans, so you can understand reality. Isn't that what you want? This is how to do it. The universe says, if you're using lines, you're going to end up with Einstein's hyperboloid inside-out superhyperbolic system, which does not provide understanding because the universe is not constructed the way Einstein showed us. He found a derivative solution which is very good for space travel, and that's all it's good for. The rest of it is a problem, and it interferes with our direct perception of the quantum paradox, because it supposedly violates relativity. Well, something had to. Something had to violate that stupid system. It's only good for navigation, to coordinate signals between craft that could be hours away from each the Earth being one craft, where you're sending a signal to your Pioneer probe, maybe approaching Saturn, maybe it's the Cassini vehicle, and you need to tell it to make a right turn at this ring because you want it to get closer and it's got to fire its thruster. Well, you have to compute a 3-hour time lag. And you can't do that without supercomputers because the only known way to compute that time lag is with Einstein's field equation, which works. And it's also just conveniently a definition of gravity, because it's gravity that curves space-time. Did you know that? Is that true? No. Because time doesn't curve. Does space? You could say yes or you could say no, but no matter how you formulate it, you run into a very strange paradox which has just blown the minds of anybody who considers it, which is if you're trying to understand the structure of the universe from the Einstein field equation, you would think that time is perpendicular to space. It's not. Although, actually, it is. It is superpositional, and this is part of the paradox. Is time perpendicular to space? Only if you're using linear systematic development of volume space going to hypervolume space, which is what space-time is, but you began with a line, which means that now you need 4 lines, and that means that you have to shoehorn time into the linear system as another dimension, which has to be perpendicular. Well, since you're just looking for a direct proportion between time and space, you can construct it that way. It's the same thing that James Clerk Maxwell did to organize his perception of electroforce in relation to magnetoforce. They're perpendicular. But are they? In both cases, yes, but you actually can't see it if it's cubified, because it makes a hard right angle where they meet, and that produces the quantum paradox on the reduction of the angle to 0. That can be solved by reparameterizing the plane to a circle, which from thence, instead of cubifying volume space on a squared plane, if you have a circularized plane, which is called a polar projection, by the way, the circles are concentric around a middle point, like on a radar screen. And so distance, you could say, is in all planar directions. Well, that's called an integral. That's the integral of the linear distance. When you rotate that radius all the way around, you get the integral of that radius. And that's called the circumference. That can be extended to the sphere in a strict mathematical relationship. But all of this is beginning with the linear grid, which is an extrinsic geometry. But if you parameterize the plane with a circle instead of a straight line, actually two straight lines, instead of using two straight lines to parameterize the plane to get a distance metric for the plane, you don't use two straight lines. You just use the circle. And the circle gives you the distance, but you have to figure out the direction. In normal computation, you're trying to get the direction. But what if you don't need the direction? What if you're measuring force? What if you're measuring the force of a proton on its surrounding space? What if you're measuring the presence of an electron in its surrounding space? Then you need spherical geometry, and you can immediately see that that is actually the only way that you're going to get a direct match, or the closest approximation. If you use straight lines, you have to take a derivative to get a rate. That's what this family of curves implies. None of these lines are straight, but one family of them is closed, so it makes an interior. The hyperbola does not make an interior. You could say it makes an up and a down, and there's actually, that is true, but it's not closed. The down is open. It's called an open geometry. The straight line is the classical open geometry because it goes off in two opposite, called polar directions. So that's plus and minus. But a curve does not have plus and minus in the same sense because it's not straight. So it doesn't know what polar is directly. What does it know instead? It knows in and out. When you have a circle, you have the concept of in and out, which is how we see. When you look at something that's small, you try to get your eyes closer to it. But if you're looking out into the universe, you're looking up into the night sky. Even as a photograph, you're looking into the night sky, you're looking out. That's circular out. Actually, that's physical out. It's spherical out, which implies a center. Well, normally we would either say that's the person, the telescope, or the Earth. But if you're using a barycenter, it's somewhere near the sun, where everything balances and everything actually goes around this point, which you can imagine is close to the sun. The barycenter, the actual gravitational center of the solar system, is not the center of the sun. It would have to be off by something because of the planets that are affecting the gravitational curvature, correct? So Einstein's relativity makes sense, even geometrically, when you consider the flights of the planets around the sun. So all of this has to do with angular momentum. Because of the presence of a gravitational center, this makes centers in the universe, centers of space. Well, what's the quantum of that? That would be the quantum of gravity. That's the proton. That's the quantum of gravity. That's the space particle, because it has an effect on space, which we can measure. And it's the definition of gravity. It's the smallest unit of gravity. So that's the quantum of gravity, is a proton. And all protons are alike. So that's the space quantum. So we have a metric for space based on the quantum, and that would be the center of a frame of reference based on a gravitational center in space. A proton makes a black hole in space. It makes a black hole in space. A moment's thought will convince you of that. Where is it dragging space? It's pulling space in, right? That's called gravity, because if another material object, a mass object, like another... See, when protons get together, their force fields overlap, and that's what creates gravity, is the number of protons. That's been proved, but it's not often emphasized. We already know what the quantum of gravity is. That's the graviton. Well, that's the proton. The proton is the graviton. It's the quantum of gravity. There is no other. There couldn't be. So what's the electron? The electron is a particle that exhibits the exact conjugal opposite of what the proton exhibits. And the electron is attracted to the proton. That's because the proton is curving electronic space. The electron sees the curvature. In other words, the electron responds to the curvature of space, which for the electron is exactly that. It's the curvature of space. And the curvature is a force field that attracts the electron. So when the electron gets close, it's just like a planet getting close to a sun in those Gedanken experiments. What if a planet is just wandering, and here's a star and it's approaching the star? Well, it goes into orbit. Maybe. It could actually, the planet could approach the star and go on a hyperbolic trajectory, indicated by the blue line. There's not enough attraction to capture it at its velocity. So it approaches on one side of this hyperbola, which is symmetrical, and when it reaches its closest approach to the sun, it keeps going because it has enough velocity to escape orbit. And that is a perfect hyperbolic trajectory. Comets have been noted to be hyperbolic, which means that they are not orbiting the sun, they just happen to get close to the sun, and they executed a perfect hyperbolic trajectory to get away from the sun on the other side. A perfect symmetry. So that is the family of hyperbole seen in celestial mechanics. There is also a parabola. That's the green line, which is quite unique because it's the separating curved line between the hyperbolic system and the elliptical system. What happens as the parabola is made to have its two arms get closer and closer, called an attenuation, until they're almost vertical, and then they become vertical. That is, they go to infinity going in and snap to verticality. On the symmetry, they snap to their axis. That's the collapse of the wave function. That's the collapse of the hyperbolic wave function into an elliptical wave function, which is a continuous curve, as proved in this next diagram, which I'm getting to. The Boschkovich force curve, that is the diagram of the Bohr atom before the Bohr atom was discovered. So those are electronic shells. Each one of those humps is a Lagrangian point in a multi-body system where the mini-bodies are collected together, called a nuclear core of protons. We'll get to the neutron later. That's actually an interesting case, which is always brought up because it's absolutely confusing. So we don't deal with the neutron. It's not necessary to. The neutron is a proton without charge. So now we have the Boschkovich force curve, which can be reduced to this for one single proton and electron. Ruger Boschkovich, who discovered that force curve in the 1700s, never reduced it to this because he didn't know what a particle was. He just gave the particles particle quality, whether it's a proton or electron. He had no way of knowing that there were two different particles, which is quite confusing even to physicists today. That what's the relationship between particles? It depends on which two, because the proton and the electron have a force curve relationship that's depicted here. Although this is not the depiction of the force curve relation between a proton and an electron, although it looks like that at its innermost curve on this one, where the innermost curve is this one labeled F, and I just want to expand this a little bit so you can see that. It's germane at this moment. That innermost curve, F. Here's the pointer, this one. You see it dips down, and then it dips back up and skyrockets off to infinity. That part of the curve, that segment of the curve, is this. So let's, I'm sorry, let me just readjust this here, if I'm able to do so. So, give me a mo. Now, I think that's almost back to normal there. So this is part of the Boschkovich force curve, but it's not for a proton and electron. It's for two protons. This is a diagram of the strong force, because a proton is repelled by another proton, but that's not what this shows. Inside that spherical limit, where a proton continues to repel the other proton, if the approaching proton has sufficient velocity to overcome the electrostatic repulsion, it will come to this curve, because now it's being attracted as if it were an electron. And this is so the two protons can bind. And this is the binding radius of the two protons. This is a radius. The radius can be seen right here. That's the radius of the center of the inertially static proton, which is considered to have no velocity for convenience. And this proton is approaching on this trajectory from right to left, and it's accelerating, 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 and now the force valence begins to curve to its opposite. So less and less acceleration, less and less, it's actually decelerating, and when it reaches here, it has to have velocity to keep going. If its velocity is very high, which it was back here, by here, if it still has velocity, then the force relationship is repulsive and it goes to infinity in a very short distance, which the proton cannot break. This force curve shows that the two protons will not collide. They won't collide. In the Hadron Colliders, you force them to collide anyway by giving one of the protons an artificial amount of velocity using magnetism. And that's how it's done. A cyclotron is what it was originally called, having enormous magnets. So that is to accelerate a proton to defy nature and break this barrier which nature has declared. And that's enough for now. That's a little over 45 minutes. So this is our introduction to the family of curves, which I now have the mathematical system which replaces Euclidean geometry with a new number system that is a nonlinear number system called the dyadic fractions, the powers of two which run your computer. And I just want to leave you with a brain teaser, which I hope you enjoy. The most beautiful formula in all of mathematics. I used to think that it was e to the I pi power equals -1. That is most often considered to be the most beautiful, but there is one more formula which is far more profound and actually unlocks a lot of the secrets of physics and mathematics, ultimately everything, because this introduces the conjugal universe, which has an imaginary space which everyone can see who looks, but since it's imaginary, it's hard to geometricize. I have geometricized infinity, and now it's rational. And that, of course, is the greatest breakthrough in the history of science. Thank you for tuning in. We'll be back with more of the family of curves and the new number system, the base 2 number system, whose most beautiful formulaic axiomatic mathematical formula is 2 to the 0th power equals 1. 2 to the 0th power. 2 multiplied by itself 0 times equals 1. That has been proved. And I've been able to use that in conjunction with Emmy Noether's force symmetry balance. A conserved force is a symmetrical force. There's a symmetry everywhere. And when you have gravity from a proton, that's centripetal force with respect to the electron, but also with respect to the proton at close range. It's centripetal force. They attract. The electron is attracted to the proton, but it goes into orbit. That's a right angle in spherical space, and that's the right angle of energy out of perceptual space into angular momentum system space, which is where time lives, because time is a derivative of energy. And what Einstein actually showed indirectly, which I've been able to integrate into the correct solution, reformulating Einstein's spherical, actually his pseudo-hyperbolic linear extrinsic geometry based solution for space-time, I now have this solution for space energy. And those are the two domains, one of which incorporates imaginary space, but they both do, but they conjugate and become rational. And this is the rationalization and dequantization of both time and space. You could say that both of them curve, and I've proved it. But it's interesting how time curves, because that has to do with the quantum relationship. And that finitizes the universe, so now it's fully computable as we wanted it to be, but only if you use the base 2 number system, which is essentially the subset of the linear number system called the fractions, but it's a subset of those. It's the rational fractions. It's a subset of those. It's the rational fractions that are invertible, such that the multiplication of the conjugal relationship between the two numbers, 1 over 2 and 2 over 1, multiply to 1 over 1. 1 over infinity times infinity over 1, what does that multiply to? It multiplies to 1. That is the quantum circle and the quantum sphere, depending on your projection. In space-time, it makes a sphere and a countersphere called hyperspace. And that's the barrier that nobody's been able to see into. You can now see into it with supervision. You can now turn on your hyperspheric visual system if you choose, but there is a certain, I'll just say, legendary risk that you could lose your mind. Every scientist loses his mind when he discovers something new, because nobody is going to accept it, because it's new. But you know it's true. Well, how did you figure that out when nobody else did? You lost your mind, but you came back, and you always come back. Unless there's a footnote, like for guys like Cantor, we're not sure if he lost his mind trying to quantize infinity. I've done better than Cantor ever could imagine. All these guys have forgotten geometry, but I didn't. I'm a dunce cap. I don't understand mathematics very well, but I certainly seem to have an aptitude for geometry. Well, that revises our Euclidean number system, so now it works. We lose 0, we lose infinity, which are the two main nuisances of linear mathematics. We don't have those anymore because we're using the number system that the universe uses to compose its structure. And that's the answer. It actually unifies gravity and electrodynamics on spherical orthogonality, but it's transdomain. And that means you have to go to Lulu Land. We'll do that in the next video. Be sure you have your compensatory medicine ready, whether that be beer, marijuana, perhaps something in a pill form. It doesn't matter. Do what you have to do, but get ready to go to the edge of the universe and temporarily beyond, which would either make you godlike or demon-like, or certainly you should lose your mind in some way. Yeah, but you'll get it back better. And that's called physical wisdom. Thank you for tuning in. We'll be right back on this last day of May in 2026. I hope you're having a good approach to the equinox. Well, we're passing to summer. And then we'll be approaching the solstice, the summer solstice, and this will be the hottest summer in the history of the Earth. Although you may want to check into that to see how far back does human time go, where we would be able to feel the temperature of a summer. About 10 to 20,000 years. Before that, the Earth was just rolling around lifelessly. But then the angels came. Oh, well, we won't go there, but we will prove that science can validate that story, certainly, which is actually what really happened. Whether you know that or not, hey, get out your rosaries, go vote, go to church, do what someone else tells you. Don't ever use your own mind. But all the great scientists learned to use their own mind. And if they're very good, they're determined, they will volunteer to lose their mind in order to make the breakthrough that humanity needs to get the answers for real life, called reality. Quite complex. You need rational logic to give yourself choices. Thank you again for tuning in. We'll be right back.